Thank you, Sean, and thanks, Raphael, for the last-minute invitation. It's nice to be so close that I can come and say hello to you all so regularly. Yeah, so I'm going to be talking about actually two papers that appeared over the last few months, one that just appeared on Sunday. So probably most of the talk will be about the first paper, and we'll be talking about things that are going to seem, I hope, very simple and basic. And if you're sort of going along and saying this is super easy, then that's the point, and I've achieved it. This is taking a limit of physics in AdS where there are lots of problems that we're trying to understand, and putting it in a setting where we can understand the bulk using basically undergraduate quantum mechanics, non-relativistic quantum mechanics. Yeah, the second paper is, in that context, bringing to bear some tools of CFT, so namely the T-channel conformal block expansion and the Lorentzian inversion formula. That second paper is perhaps a little bit technical, so I'm not going to go through all the details of that, but just want to give you a flavor of the main ideas and main sort of interesting novelties that we come across there. Okay, so without further ado, let's just start off by explaining what I mean by this non-relativistic limit of AdS. So here, this first line is the metric of Anderton-Sitter space in global coordinates. And we know from our first course on general relativity that there's a Newtonian limit of GR where the important actor in the game is the GTT component of the metric. And that GTT component of the metric is 1, like you'd have in Minkowski space, plus some small correction, and that correction is just the Newtonian potential phi divided by the speed of light squared. So if we take this example for AdS and just read off the Newtonian potential, then it's just a quadratic function. It gives us a harmonic potential harmonic gravitational potential for particles. And the important parameter here that I'm going to hold fixed in this limit, so I'm going to take c to infinity, but hold fixed not the AdS length, but rather the AdS time, or the AdS frequency, which is the speed of light divided by the AdS length. So we know that AdS acts like a box, time-like geodesics are all periodic, and that period is some fixed unit of time, and that's 2 pi over omega. So that's the thing we're going to hold fixed. And okay, that means that any particle of mass n that moves in AdS non-relativistically has this extra quadratic harmonic potential. On top of whatever interactions it has with everything else, every particle will have this universal potential that depends in this way on its mass. And okay, when is this non-relativistic limit actually self-consistent? There are a few different ways of saying it. These things are actually all just equivalent, just give slightly different physical pictures. So the first one is saying that mc squared, the rest energy of the particle, should be bigger than the typical non-relativistic energy of the system. And that energy is h bar omega, which is this familiar quantum of energy in the harmonic oscillator. Another way of saying it is that the AdS length is got to be large compared to the sort of typical relativistic quantum length scale of the particle, which is the Compton wavelength. Or another way of saying it is that with this harmonic potential, any particle will have some Gaussian wave function with some width. And we'd like that width to be narrower than, to be smaller than the AdS length, L. So what we'd like to be doing here is keeping hold of this omega, but taking the AdS length to infinity. So we don't have to worry about the spatial curvature. It's only this sort of GTT piece, the harmonic potential. Okay.
Way to quickly just say what exactly, are you just scaling C and L to infinity while holding omega fixed?
Yes, that's right. So omega is held fixed and C goes to infinity. Yes.
So this is you're holding h bar fixed, all of these inequalities will be satisfied.
Yes, exactly, yeah. So C goes to infinity guarantees that all of these things will be satisfied, yeah. So C goes to infinity, L goes to infinity with omega fixed, ratio fixed, yeah. So okay, these inequalities are all actually the same thing, but we can express them in the language of CFT, which is in terms of this dimensionless quantity, which is the scaling dimension of the operator dual to some particle. And that scaling dimension just has to be much bigger than 1. That's the the relevant thing. There's also this mc squared over h bar omega is some large thing. There's this correction d over 2, and that d over 2 is just the ground state energy of a harmonic oscillator. Right? So there's d harmonic oscillators, one for each spatial direction. Each one of them gives you energy h bar omega. Together they give you this d over 2, and that's actually, if you take this familiar equation that we learned on AdS CFT, that m squared is delta delta minus d, and you expand this, that's a large delta, then you'll get exactly this d over 2. But it has this very nice, simple interpretation as being just the ground state energy of a harmonic oscillator. And that sort of thing will be a theme that there are many of these very, very familiar kind of cozy facts that take us back to our childhood when we all learned quantum mechanics for the first time. But they've got this sort of analog in this setting of AdS, where many of us also like to spend some time. Okay, so why is this interesting? Why do we want to study this? Okay, most of this, from my point of view, comes from AdS CFT, which is basically our best understood setting where we can study theories of quantum gravity. We know if we have a CFT with certain properties, a 't Hooft expansion and a large gap, then these are really describing theories of quantum gravity in anti-de Sitter space. We know exactly what all the observables are, and we have many tools to study this. But there are still lots of hard questions that we'd like to have a better handle on. So we've got this duality, but certainly non-perturbatively, when we're not close to empty AdS, when we have large metric fluctuations and so forth, it's not clear where the sort of space-time bulk metric variables are hidden in CFT variables. We don't really know what the space of all possible consistent theories is. Is there a theory that just looks like pure Einstein gravity in AdS? We don't really have any tools to address these kind of questions. So there are lots of different, and also one thing we'll touch on today is the L goes to infinity limit, where we return to flat space-time. Then, okay, we might look at things that happen in a small region, much smaller than the AdS scale, in the middle of AdS, and it's more or less flat space-time. So flat space-time physics is embedded already in AdS CFT, but it's hard to kind of find an intrinsic boundary definition of flat space that's as useful and as powerful as a CFT. Okay, you can just say in flat space we have an S matrix, but the power of AdS CFT comes from the fact that there's actually a local theory living on the boundary. We don't really have an analog of that so far for flat space-time. Okay, so these are hard questions, but the same questions can be asked in a more controlled and simple limit, which is, for example, the limit I'm going to study. And this has an advantage that we know how to do everything in non-relativistic quantum mechanics. The bulk, even away from perturbation theory when interactions are very strong, is under complete non-perturbative control. We really know how to calculate everything, at least in principle. Okay, occasionally we'll have to solve ODEs numerically or something, but we really know qualitatively what's going on under control. There are solvable examples, like in 4 space-time dimensions as a Coulomb potential, 1 over r, this hydrogen atoms. We can solve this, and then we've got some non-perturbative, exactly solvable thing, and we can start asking how that kind of thing is embedded in CFT. And I think another reason not to be sniffed at is it's, I think, very pedagogical. There are lots of facts that I've known for a long time about AdS physics that I just thought of as kind of brute facts, that when you embed them in this context, it gives you that extra intuition that we've developed for a long time and puts it in a really familiar setting. Okay. So I hope that motivates a little bit why it's useful to study these very simple limits. Okay, so to kick us off, we should start with a discussion of the symmetries, what happens in this non-relativistic limit. Okay, so our starting point is the symmetry algebra of a CFT. So this has this conformal group SOD2. So this is the isometries of AdS D plus 1, or just the conformal symmetries of the boundary CFT. And the important generators of this symmetry group for us are going to be these D, P, and K. So D is the dilatation operator. So if you have this acting on the D-dimensional plane, the dilatation operator is the thing that has scale transformations on that plane. And then there's the p's, which are the momenta, so they're translations on the plane. And then the k's are special conformal operators. And they obey this algebra at the top, and the m's are rotations. The mij's are rotations here. Okay, D is Hermitian, and the momentum are conjugate to the special conformal transformations, the Hermitian conjugates. Okay, so to take the non-relativistic limit, we write this dilatation operator as, so this dilatation operator, I should say, is in global AdS. So AdS, when we write it like this soup can on the top right here, has time going upwards, some radial direction out to the boundary, and then angles. And this dilatation operator is just a Hamiltonian in this time direction. So we're going to write this Hamiltonian as a rest mass piece, mc squared, plus some non-relativistic Hamiltonian on top of that. And we're going to take c to infinity, which means this non-relativistic Hamiltonian is going to be small relative to the rest mass piece. And we're going to say that this rest mass piece is central. It commutes with everything. So this is just exactly the same way you would get from the Poincare algebra to the Galilean algebra. We do this in CFT. And okay, the first two things are basically the same. So this one way of saying it is that P acts like a raising operator, it raises energies, and K acts like a lowering operator, lowers energies. But then the thing that's novel now, usually in CFT, the commutator of K and P is the dilatation operator. But now the commutator of K and P is going to be a constant, or this central element, think of as a constant. And you might look at this and say there's raising operators, there's lowering operators, and the commutator of raising operators and lowering operators is a constant. I know such an algebra. This is Patrick Stewart as Macbeth, who's seeing the momentum generator and asking, is this a dagger which I see before me? For those of you who know your Shakespeare. And yeah, this is really the algebra of the simple harmonic oscillator. So P, after some rescaling, becomes a creation operator. K is the annihilation operator, and H is the Hamiltonian. So this is the algebra that controls the harmonic oscillator. So in this very, very abstract way, by doing the symmetry reduction, this Wigner-Ononu reduction, we see how this harmonic oscillator comes out just from symmetries.
Can you just go back and say, do you want us to think of this in the Lorentzian picture, or when you said dilatation operator, it's sort of suggested?
Yeah, so it's the Lorentzian picture, yes. So yeah, so the names come from their action on the Euclidean plane, but really we want to think about these as in sort of radial quantization. They act on a sphere, and we can think of that sphere as being the spatial slice of a Lorentzian cylinder. The sphere times Lorentzian time. So yeah, the names come from Euclidean plane, but really that's why there's these funny K dagger equals P is because the hermiticity relations come from how it acts in Lorentzian signature.
And so in the K and P, we normally think of as
in, let's see, in global AdS, they don't have a super simple action in global AdS. So global AdS, it manifestly has the symmetries of the dilatation operator and the rotations, but the K's and the P's are a bit more complicated. They're roughly boosts in the, yeah.
In the algebra, did you also scale K and P by 1 over C? To get rid of the C squared?
Yeah, essentially. Yeah, sorry, this is K and P have factors of the square root of M. So there's a factor of C hiding in there as well.
And here you're assuming that the eigenvalues of Mij don't scale with C, right?
Yeah, so this is saying that yes, exactly. So the typical spin is all we're going to say is order 1 as well. Yeah. Just to take this limit. Yeah. Is there a good? Okay.
It would just be nice to get some intuition for why these are raising and lowering operators.
Yeah, okay, so maybe it'll help on the next slide. We won't talk about this abstract thing, but we'll have it as a concrete representation on a very familiar Hilbert space. So perhaps that'll help, and if it doesn't, then ask again. Staying with the abstract thing for now, we know that we can always write this dilatation operator, so this mc squared plus the non-relativistic Hamiltonian as two terms now, because we use this, we use these commutation relations. Those commutation relations are obeyed if we say that the non-relativistic Hamiltonian is like A deg A. That's the familiar Hamiltonian. So this is just a little bit of, if you write this ansatz, then the algebra we had on the previous slide is obeyed if this thing that I'm just calling H now, so this is going to be the Hamiltonian of the relative motion between different particles, this Hamiltonian will commute with all the k's and the p's. So there's something there that is designed to give the right commutation relations, which is the familiar simple harmonic oscillator Hamiltonian, and that we're going to be thinking of actually as the center of mass Hamiltonian. And then there's some other stuff which commutes with it. So all the symmetries live in this sector, and there's this other sector that totally decouples from the symmetries.
This is just you have a particle sitting, let's say, at the center of AdS, and you can start giving it a little kick so it'll start oscillating. Right?
Yeah.
That's the harmonic oscillator here, right?
Yes. Yes, exactly. Yeah. So Yes. So we can say that our Hilbert space now is going to actually split as a tensor product. And there's the center of mass piece, which are just the representations of this algebra. So they're just representations of the harmonic oscillator algebra. There's a ground state, which is literally the ground state of the center of mass wave function, this Gaussian. And then everything you get by acting with raising operators. But then that's tensored with another piece that doesn't talk to the symmetries at all, that's the relative Hamiltonian, that tells you that perhaps I can have, so whatever system I can have, say, lots of particles that all interact. I can choose the center of mass to be in its ground state, or I can kick the center of mass, but these things are all related by symmetry. So it's, yeah.
I think what I just said was kind of wrong, because if that was the right picture, then there would be just one operator. There's only a ground state, because you can push the particle this way or that. Isn't it more like you sort of excite the harmonic oscillator by pushing the particle in all directions? Is that how it works? Because otherwise there should be operators that should correspond to the raising operators in different spatial directions.
Yeah, so there are D different raising operators, yeah. So there's D harmonic oscillators, so yeah, maybe I should have made this more clear. There's AIs, the I's label the D spatial directions, so you can give it a kick in whichever direction you like. And these arrange in multiplets of SOD as well, the rotations. But then, yeah.
Like if giving it a kick in the X direction is the same operator as giving it a kick in the minus X direction, right?
It's slightly different because they're related by conjugation by time evolution, by a half period of the harmonic oscillator. They will be independent, yeah.
You're not really translating. If you want to translate it, e to the I, P something.
Yeah, we'll get to that. We'll get to find it. Yeah.
Plus, minus.
Yeah.
You have to exponentiate
Yeah.
You're not doing that.
Maybe I should get straight to the concrete representation, because maybe the abstract thing is not the most intuitive way. I'm sort of doing it backwards, perhaps. Yeah. So let's take a very, very simple potential that you would be very happy with in your undergraduate quantum mechanics class, where you write the non-relativistic Hamiltonian for two particles that interact via a potential that depends on the distance between them. Something very simple, except we also have this harmonic potential. So there's kinetic terms, a half mv squared. There's terms from the gravitational potential, that's half m omega squared, x squared. So there's terms of the gravitational potential for both particles, and then there's some potential, arbitrary potential, for the interactions that depends only on the separation between them. And we can do the usual thing that we love from Galilean symmetries, our first mechanics course, where we rewrite x1 and x2 in terms of a center of mass, which is some linear combination of x1 and x2, and a relative variable. So xcom is the center of mass location, and x is just x1 minus x2, for example. You do that very simple change of variables, and we're used to this fact from Galilean symmetry that the center of mass motion decouples from the relative motion. So the Hamiltonian splits into this piece, which is a harmonic oscillator in the center for the center of mass motion without any interactions. And then there's this piece, which is the relative Hamiltonian, which includes the interaction. And there's this slightly funny thing that the mass is replaced by this thing mu, which is this reduced mass. So, okay, hopefully you'll recall this from your sort of first mechanics courses. The kind of interesting thing that happens here is because these potentials are quadratic, despite the fact that we've broken the Galilean symmetries, or it looks like we've broken them, you know, this potential breaks translation invariance, we still have this decoupling. And the reason comes from what we did before. We haven't actually broken the symmetries, we've just deformed them. Just like when we go from the Poincare algebra for asymptotically flat space and we put it in AdS, it's still maximally symmetric, we still have the same number of symmetries, we've broken translation symmetries, but really we've turned them into something else. So we still have the same number of symmetries, and we still have this decoupling. And now we can say that the Hilbert space is going to be functions of the center of mass motion with a simple Hamiltonian governed by symmetry, and functions of the relative separation, the separation between the particles, which is not governed by symmetry, and that's where the interesting dynamics is happening. So that's why there's this split, center of mass, which is all governed by symmetry, relative piece, which is the interesting piece. And in particular, there are some special states here where the center of mass wave function is just the Gaussian ground state of the harmonic oscillator, which means it's annihilated by the AIs, all of them, which is annihilated by the KIs. But that's precisely the definition of a primary state in the CFT. Something that's annihilated by special conformal generators. So that's the definition of a primary state. And then you act with all the A daggers to get to other places in this piece, in this kinematic piece. And that's just taking you to different places in the conformal multiplet. It gives you the descendant states. So one state in H relative, the interesting piece, corresponds to a conformal multiplet by taking all the different states in the center of mass.
So that original space-time translation is kind of coherent state, right? You just have to.
We will talk about coherent states in a second. Yeah, they play a key role. But yes. Yes. Good. Yeah. So you can actually translate. The difference here is that it's not the translation commutes with the Hamiltonian. It's the fact that translation followed by a little bit of time evolution to get back to the middle again commutes with the Hamiltonian. Okay. It's the fact that translation and time evolution have definite commutators. That's the important thing. Okay. Yeah. Does that make the whole symmetry discussion clearer?
Sorry, something like this was already true before we took this limit, right?
Yeah. So this is, in fact, okay.
Any system, a solar system in AdS, if you look at it in different frames, and some of them it looks like it's swinging back and forth.
Absolutely. Yeah. Okay. So I hope this diagram's legible. Yeah, there's a nice way to think about this whole limit as just in terms of the different symmetry groups that we have. So we have our sort of master symmetry group, which is relativistic physics in AdS, SOD, the conformal algebra. And there's something that's very, very sort of familiar that people will know and love, which is you take L goes to infinity with sort of the speed of light held fixed, say. Take the AdS length to infinity, and what you get is the Poincare algebra. So there's an Inonu-Wigner contraction of SOD, that gives you Poincare. And then you could take the Poincare algebra, and again, something we know and love, take C goes to infinity, and you get the Galilean algebra, or its central extension, Bargmann algebra. And that describes ordinary, say, non-relativistic quantum mechanics. What we're doing is we're sort of going in the opposite order. We're first of all taking the C goes to infinity limit, but we're fixing omega, and we've got this new symmetry group. Okay, it's a very familiar thing, is a harmonic oscillator algebra, and it describes this non-relativistic physics, but with this harmonic potential, which is going to have lots of analogous features to AdS. And then, of course, you can take this flat space limit. So what we're doing, this whole exercise, is filling in this, what is this bottom left corner? So it's very natural. It's like a maximally symmetric system, and it's got lots of sort of very nice natural features. It's got some very natural sort of analogs of, here there's an S matrix, here there's an S matrix, here there's CFT correlation functions, and here there's something else. So we're going to sort of fill in that gap. And we'll also talk a little bit about this limit. Omega goes to 0 because this limit helps inform us about this limit. This is really the interesting one, but this is a toy example that helps us sort of explore some of the features where we really understand everything that's going on non-perturbatively. Okay, there's the symmetries. Okay, so what are we going to actually study now? So there are two sort of categories of things that we can study in this system. There's one piece which is the spectrum. What is a set of states? Which is sort of dual to the question of what's the set of operators in the dual CFT. And then we can ask about correlation functions. What do CFT correlation functions correspond to? And these are, of course, related to each other, but these are the sort of main two things that we'll be interested in. So we're going to stick with this two-particle interaction case, first of all. And the spectrum that we're interested in is going to be what we describe in the CFT as the spectrum of double trace operators. So this is the two-particle states in AdS. So these are roughly things that are products of the operators dressed with some derivatives. And the spectrum of these double trace operators is going to be related to the spectrum of this Hamiltonian, this relative Hamiltonian, by this sort of basically delta 1 plus delta 2 gives you the rest energy. There's this shift d over 2, and then there's the energies that come from the Hamiltonian, the relative Hamiltonian. Good. Yeah, and the other piece of data here is 3-point functions or OPE coefficients. And these will have a natural analog in our setting as well. So it turns out that we can diagonalize our relative Hamiltonian, we can write down some wave functions, solve the Schrodinger equation, and these OPE coefficients, the 3-point functions between O1, O2, and this family of double trace operators, we'll be able to read them off by looking at the tail of the wave functions. Okay, and a convenient way to sort of depict these is you can draw all the possible energies as a function of spin. And you can allow spin to be some continuous variable, and the possible energies lie in these curves. These are the Reggie trajectories, it's a piece of jargon. It's just saying for some fixed spin, you have a ground state, the first excited state, second excited state, and so forth. And n here labels which Reggie trajectory, and it's just the number of zeros in the wave function, number of nodes. Okay, so the other thing we're going to discuss are the correlation functions in the dual CFT. So, okay, the interesting thing for us will be some 4-point functions. So we've got these operators O1 and O2 that are dual to these particles in AdS. And it turns out that the non-relativistic limit tells us something about these 4-point functions where the cross ratios are small. The cross ratios are of order 1 over the mass. 1 over the dimensions of the external guys. And the dimensions, remember, are large, so this is some small cross ratios. And it turns out that this correlation function, which we'll explain in a moment, is described exactly by some matrix elements of these things alpha, which roughly speaking are coherent states of the harmonic oscillator. And this is something that's, okay, again, very natural, behaves nicely under all the symmetries and so forth. Okay. And then we can also relate these two things, right? So the correlation functions in the spectrum are closely related to one another. The thing that relates them is the conformal block decomposition in the language of the CFT. In the language of the quantum mechanics, it's just summing over intermediate states. You can insert a complete set of eigenstates here. And then in the very last part of the talk, if we get there, there's a way to go back, start from the correlation function, and get the spectrum in a nice way which is this thing we'll call the Lorentzian inversion formula. It's usually called the Lorentzian inversion formula in the CFT literature. And then, there's something else that we don't have in ordinary non-relativistic quantum mechanics, which is crossing symmetry. And we can think about not the sort of intermediate two-particle states, eigenstates, but rather the things that are exchanged in the T-channel. And we think about the stuff that's exchanged in the T-channel as being whatever operators mediate the interaction. So maybe our two particles have some gravitational interaction, like some Newtonian potential, and that means they exchange a stress tensor to mediate that. Or they exchange sort of multiple stress tensors or whatever it might be.
I'm sorry.
It's the big picture.
Really elementary things that Trudy said, but is there some sense in which we can understand the non-relativistic limit that you're taking as a specific truncation of the CFT? What is that? And the objects you're writing down now live in that truncated theory?
Yeah, so we're describing a sort of specific sector of the CFT. So what we're describing are, we have some heavy operators with large conformal dimension. These create some heavy operators in AdS, so they can be described non-relativistically. And then we're describing excitations on top of that, but the energy of the excitation is small relative to the energy, the sort of inherent energy of the operators. And there's some assumptions in what kind of theory we have, that these things don't decay, and so forth. But it's that sort of narrow sector of the theory where we're looking at those excitations on top of them. So we're looking at, in the bulk language, some sector of fixed particle number without too much kinetic energy, say. So that's sort of the big picture, the things that we're going to be attacking.
So what happens to operators? So the heavy states are like the rest masses of the particles that you put into your system, right?
Yeah.
And what happens to photons and things like that? What happens to operators that would have created photons?
Yeah.
Do they just
Yeah, so we could also have operators here that are not just the double traces of two particle states. You could also include operators dressing this with extra currents and stress tensors, which would say we don't just have our two particles, but we have some photons hanging around or gravitons and so forth. But the leading order in the non-relativistic limit, those decouple. The radiative sector decouples from the so there's a Coulomb sector, say, of the interactions that's important, mediates some potential, and then there's a radiative sector, and the radiative sector is just free excitations on top. Decouples is not. So it's definitely interesting if you want to include corrections and include, hydrogen atoms can decay and all these kinds of things. But the point is they're small effects.
It's not suppressed by the limit, it just decouples.
Well, it's decouples in the C goes to infinity limit.
Yeah.
But this is the same in ordinary sort of flat space quantum mechanics. But yeah, no, thanks for that's a useful clarification. Yeah, so you can always, so maybe this Hilbert space on the top right, maybe there should be another tensor factor that includes the radiative stuff, and the Hamiltonian would mix with that, but the mixing Hamiltonian is small. So we just ignore it for today. But it's in my list of open questions, so it's something that's interesting to add in. Okay, so let's talk about these correlation functions. So the key point here is that if we want to talk about correlation functions in the CFT, we need to know how we think about operator insertions on the boundary in some arbitrary location in terms of our bulk theory. So there's one easy thing that we can do, which is we have this, our cylinder. We'll think now about living in Euclidean signature. Useful? And we'll imagine we have our global AdS cylinder. We can insert an operator at the negative infinity Euclidean time, and inserting an operator down there just corresponds to creating a primary state, if it's a primary operator. So that's this primary state, is operator insertion in the infinite past. We can do this exponential map that takes our cylinder to the plane that we're sort of familiar with. There's this radial quantization story and yada yada. So okay, this will be familiar if you like your CFT. So on the plane, it looks like this. We're interested in states on this sphere, the red circle. But if we wanted to move our operator from the center, where it's creating a primary operator, to somewhere else, we have to translate it, that is, act with e to the momentum operator. And remember, in the non-relativistic limit, the momentum operator becomes a creation operator. So it means that on the cylinder, this translation operator moves the insertion down from minus infinity up to some finite Euclidean time. And that corresponds to changing the wave function, sort of boosting the wave function to a coherent state, which means it's the same Gaussian wave function you'd have, it's just offset from the center. So it's some stationary particle, but it's sat up the potential, and if you let it go, it'll run down and so forth. Okay, so that's if you had one particle. And if we do two particles, it's very easy if these things don't interact. We play the same game. Two operator insertions is a product of coherent states. But there's the nice thing that we can actually choose these insertions in a judicious way. That means the center of mass is the ground state, and the relative piece of the wave function itself is a coherent state. Okay, so that's, okay. The details of that are not super important, but the upshot is that inserting two operators creates a coherent state in the approximation they don't interact. If we want to, we can actually upgrade this to a state even if the particles do interact by playing a similar game to what we do in scattering theory. You know, we define scattering in states by saying they're plane waves, but not sort of at time zero. They're plane waves in the distant past when they're far apart. So we kind of evolve backwards with the interacting Hamiltonian and forwards with the free Hamiltonian together, or other way around. So you start with free plane waves, evolve backwards for a long time with a free Hamiltonian, and evolve forwards for a long time with an interacting Hamiltonian. And that's how you define in states. We play the same game here, except it's slightly different. It's in Euclidean signature. Okay, the details of this maybe aren't super important, but okay, there's a natural way to define these states, a bit like scattering states, but they're now not plane waves, they're coherent states. Okay, so we've got these coherent states that correspond to operator insertions, and if we wanted to take some inner product of these kind of coherent states, then that builds a 4-point function for us. So we get some particular 4-point function is a matrix element of these guys. Right. And we can include a piece of real-time evolution in the middle as well, if we like. And that sort of generalizes the kinematics a little bit for us. Yeah, and okay, it turns out that the cross ratios are these small things.
So
it's in the details.
Is broken by your scale, right? Rescaling and so on. And
yes.
So for that, it depends on position to
yeah.
Yeah, and then we just have to compute
yeah.
Initial wave packet to be.
So
And a final wave packet to be.
Yeah, so okay, the idea here is that there's okay, you insert these operators, they create some particles that live near AdS. You do some time evolution, and for a while, these particles are far apart near the edge of AdS, so they don't interact very strongly with each other. Eventually, they'll get close enough that they interact. And like at t equals 0, where we're defining the states, maybe they're interacting. But there's this region of overlap where they're both moving non-relativistically. So the Euclidean time evolution sort of sucks the energy out, so they start moving slower. So at some point, you enter the non-relativistic regime. And the crucial sort of assumption here, I guess, which tells you how strong the interactions can be, is that there's an overlap between these, so that they get close enough that the non-relativistic limit is valid. So they get a distance that's much smaller than the AdS length before the interactions become strong. And that's actually there's just a self-consistency condition of if this limit exists, it's self-consistent, it makes sense. Yeah, that's the picture. Okay, so that's the idea. Let's just very briefly go through this. Maybe I don't want to go through it too much. But okay, you can now calculate these things, so you can relate the spectrum OP coefficients in the usual way. You insert a complete set of states, labeled by NLM. So there's some spherical harmonics, and there's some radial wave functions, and okay, away you go. And the overlap, crucially, between these coherent states that I've defined and the eigenstates, because we're doing this thing where we define them in the asymptotic paths, where they're far apart, is determined by the tail of the wave function. In particular, there's just a coefficient here. So the tail of the wave function is determined by the Schrodinger equation, and there's just some unknown coefficient. The square of that coefficient is the square of the OPE coefficient that appears, well, okay, the square of this appears in the sum over states, and now that sum over states on the nose gives you the S-channel conformal block expansion. So, okay, there's a calculation to do, which is compute the S-channel conformal blocks, okay? It's a tricky exercise in this limit, but you can do it, and it really just identically gives you the sum over states. And the descendants actually drop out for exactly this reason of decoupling between the symmetric sector. So, you know, okay, there's some like Legendre polynomials, and there's some times, and there's these coefficients. And, okay, you can actually do this exercise. You definitely can't read this equation, but that doesn't matter, because the only reason to put it there is say it's a complicated product of loads of gamma functions. You take the non-relativistic limit, which means large dimension, and that simplifies massively. The only thing it depends on is delta 1, delta 2 divided by delta 1 plus delta 2, which is this reduced mass. So you have this complicated formula that takes lots of clever people, many papers and pages to derive. You take the limit, and out pops this coefficient that you recognize from your first course in mechanics, which is kind of fun. Okay, so I'll just briefly touch on one interesting limit here, which is what happens when we take flat spacetime. So we take this harmonic potential to be very, very shallow. So we take in C to infinity first, but now we're going to take omega to be small as well. And the spectrum now divides into sort of two pieces. There's the stuff that would have been bound states in flat spacetime with negative energies. And then there's the stuff that would have been scattering states, but now there's this potential that they sit in. So like a scattering wave function might look like something like this. There's a scattering region where you just have to solve the Schrodinger equation. There's a region where there's plane waves, so it goes like the cosine of k times r plus a phase shift, and the phase shift is determined by this scattering region. But then eventually it hits this shallow potential once it gets very, very far out. And there has to be a match so that when it hits this potential, the wave function is purely decaying. So generically, it would have a decaying part and a growing part. If this wants to be a physical state, that growing part needs to be 0. And so that gives you some condition, which looks like you can't read very well. But the upshot is that the spectrum of operators in this limit is related very, very directly to the scattering phase shift. So the relationship is the anomalous dimension, which is how much the dimension shifts from what it would be in mean field theory or free quantum field theory in AdS. That shift of the energy is exactly proportional to the scattering phase shift. It's a very, very simple relation. Things like this have appeared in the literature before, but in more complicated ways that average over energy windows and various other things. Here it comes out very, very cleanly, and in particular, several places this has appeared in the literature has been as a first order in perturbation theory when the phase shift is small. Here the phase shift can be very big. It's a non-perturbative statement that's exact in this omega goes to 0 limit. So there's a very, very clean relation between the spectrum and the flat spacetime phase shifts. Good. So that's the spectrum in flat space. There's also a nice correlation function in flat spacetime, where we take this time evolution to be exactly time pi in AdS units. So what the picture here is that we start off with some Euclidean part of spacetime that prepares these coherent states. And these coherent states are sort of far apart. They sit somewhere up this harmonic potential. And then we do some real-time evolution. We let the particles go, and they just get accelerated by the AdS potential. And then they meet somewhere in the middle with some velocity that depends on how far you put them up the potential. They scatter, they come back out again, and then you take the overlap with a final state. And that way you very, very directly, in this very physical picture, measuring a scattering amplitude. You know, okay, there are people who've talked about, okay, this is not completely novel, actually. There's a paper by Elliot Hijano that does something very similar, and also a paper by Shoto Komatsu. So that's not in the non-relativistic limit. It's playing a similar game to this. But anyway, the upshot is you literally have a 4-point function that is equal to a scattering amplitude.
You prepare, just maybe summarize it to
Yeah.
see if I understand. You just prepare with coherent states, and you, of course, you put out the relativity figure, and then you just kind of project onto eigenstates of the dilatation, and then in each one is just your scattering phase because it's just eigenstates of the dilaton.
Yes, yeah, so that's technically how we show this is true. Yeah, so again, the advantage for us is that so most of this work previously has been working in perturbation theory and stuff like that. We can show this non-perturbatively without, and we really have nailed down all the caveats, exactly when this applies and when it doesn't, by doing precisely what you say. You just insert a complete set of states. Those complete set of states, this time evolution, just becomes e to the 2i delta. And then e to the 2, all you have to do is sum over spherical harmonics to turn that into a scattering amplitude.
Going back to the basis of the coherence.
Yeah, yes, yeah, that's right. Yeah, so the coherent states are important because they tell you that the sum over n, the sum over different Reggie trajectories of fixed spin, is actually dominated by some saddle point that has some width. And that's where the coherent state wave functions and OP coefficients are important. Yeah, but okay, this is the upshot. You literally got 4-point function equals scattering amplitude. With some simple kinematic factors. It's not, like you can get it from Mellin space, for example, but that's much more indirect and it's sort of looks more complicated.
So all these delta you need a still theory.
Sorry?
To get all these delta, you still need a theory. Delta F.
Yeah, so you can, okay, so here's an example of a theory, the theory that I can solve, which is the Coulomb potential. And okay, I won't go through all the details of this because I want to get to some of the good stuff at the end. But okay, there are various pieces of the spectrum. This shows you the full spectrum of the theory. Any value of the spin, we can work out what the energies are, plot them, and down here there's bound states, the hydrogen atom. If you go to large enough values of large enough angular momentum, L much bigger than 1, then the hydrogen atom turns into classical Keplerian planetary orbits that we know and love, elliptical orbits. This axis, the n, which state you're at, tells you how elliptical the orbit is. In this piece of the spectrum, it's all governed by scattering theory. It's governed by Rutherford scattering. And then on the right-hand side, that's where the harmonic potential starts being important, and the quadratic potential becomes the leading order piece. So down here, it's all dominated by the Coulomb interaction, and you can think of the harmonic piece as a small correction. Over here, it's dominated by the quadratic potential. The Coulomb is a small correction. So this is like free field theory plus some perturbations.
This you got too much to the Coulomb.
Sorry?
This you got too much to Coulomb potential, right? Input is a Coulomb potential.
Yeah, so the input is the Coulomb. Yeah, so this is a bulk. So far, everything here is a bulk calculation. So it's doing the non-relativistic thing with this G over R in AdS4.
Then you got the property of the CFT.
Yeah, so the last part, we're actually going to talk about how to get this piece from the CFT directly in the last 15. Good, okay. One more thing that's kind of fun is resonances. Maybe I won't talk any detail about this, but okay, resonances, unstable states, these are some non-perturbative phenomenon. You can never get these in perturbation theory. And there's a nice picture about when you have a resonance, it sort of manifests itself in this reconnection of Reggie trajectories. And okay, you can ask me about it if you want to. It's a sort of fun application. And actually I think that's more, I've always been a little bit confused by when you have unstable particles in AdS, exactly how that resolves into a spectrum and so forth. But this really answers it very, very cleanly. Good. Okay, so the last part, maybe it's a good time to pause for questions on on that bulk non-relativistic piece, but the last part, we'll just have a couple of slides. I'll sort of go a bit more slowly because it's probably more unfamiliar, talking about the CFT side of things. Are there any questions so far? Okay. Everyone's either completely on board or completely lost. Okay, or shy. Okay, so the first The first tool that we're going to make use of that we don't have in non-relativistic quantum mechanics is crossing symmetry. So we already expressed in CFT language our correlator as a sum over S-channel blocks, which has a very simple interpretation as a sum over intermediate states in our quantum mechanics. But T-channel blocks is not so obvious. Okay, so just from the CFT point of view, we've got an expansion that looks like this. Our correlation function is some free piece. So this 1 is exchanging the identity operator, which gives you the free correlation function. And then there's an exchange of a load of other junk, every other operator in the theory in principle. So these are the things we're going to think about as mediating the interaction. So thinking about a gravitational interaction, there's going to be the leading order piece is going to be the exchange of a stress tensor. Also at leading order, importantly here, there's exchanges of double traces. So before we were talking about O1, O2 double traces, which are two particle states of the different particles. Now we've got O1, O1, which are two particle states going in the sort of other direction. So before we were cutting our correlator like this, and the states were going vertically. Now we're cutting our correlator in the other channel, and we have to include these things. And maybe I should emphasize, these things are heavy, and I think a lot of people have the intuition that, which is true at generic kinematics, that these heavy operators exchanged are suppressed, and you don't have to worry about them. But because we're also going to small cross ratios, which means that from the T channel we're going very, very close to the cross channel, that's actually, these are not suppressed. These are there at the leading order. We'll see that right now. Okay. Okay, so how do we understand these T-channel blocks? So you can calculate these things in the non-relativistic limit, and it turns out that the useful way for us to understand them and calculate them was this representation that Hajano and friends wrote down a few years ago, which is something that's very close to AdS physics, which is a geodesic Witten diagram. So this is just an integral representation of a conformal block. So it's really a CFT object, but it's an integral representation that's sort of inspired by AdS physics. So the expression that you get, we can interpret it in this way. What we do is we take our potential, whatever potential is mediated by the exchanged operator, and we integrate that where the separation is a function of some Euclidean time, and that function is just the radius of a classical trajectory in AdS. Yeah, I'm not sure. Right. So this is what you would expect for if you add a perturbation to your theory, but you're just doing a classical perturbation theory. So what's the shift in the energy, let's say? Well, okay. What's the shift in the action, perhaps, working just in a classical theory? So we'll compare this with if you actually compute the correlation function perturbatively. So this thing, from the AdS point of view, is the non-relativistic limit of a Witten diagram, which is a different object from a conformal block. And these are different. They look very similar. We've still got the same integral over a Euclidean time, and there's still this classical trajectory enters in, but now we've also got a wave function that we're integrating over. So here, the variation of the correlation function includes the quantum corrections, integrating over spread of wave functions, and they're absent from the Witten diagram. So we've got this very nice, clean result that a single block, like the stress tensor exchange block, picks out the classical piece of a graviton Witten diagram. And then all the other stuff, the quantum corrections, they have to be built up out of these double traces, because these double traces are the other things that appear in a Witten diagram that looks like this. Okay. This very, very kind of clean result. It's an interesting question to ask. This is really sort of to first order in perturbation theory. Does this work to higher orders? I don't know, but it's plausible. Okay, so there's this very nice split that we can understand physically what's going on there. Okay. Now, the last couple of slides are talking about the Lorentzian inversion formula. Luckily, we're not going to get into too many details, so we can give the main punchlines. So the second tool The inversion formula it's called an inversion formula because it inverts the conformal block expansion. So conformal block expansion, we take the CFT data, the dimensions and OP coefficients, and we get out a correlator. The inversion formula does the other thing. We give it a correlator and it spits out the data of the theory. And the form it spits out that data is some function of dimension and spin, and the physical operators appear as poles of this function. And the residues of the poles are OP coefficients. Okay, and this formula is interesting because it's, well, first of all, it's an integral over Lorentzian kinematics. So real cross ratios corresponds to taking some correlation functions in Minkowski space. This is a correlation function of a double commutator, turns out. Got a close relation to things people study in chaos, out-of-time order correlation functions, things like this. May be familiar from that. And you integrate against some kernel. And a useful way to think about this for us will be you can do the z-bar integral first, which gives you a function of z. And the way that the poles over here appear is that a fixed power of z, you sort of do a Mellin transform, if you're familiar with you know, if you like those kind of things. But anyway, some fixed power of z immediately gives you a pole. So this thing, by just doing the z-bar integral, is a generating function. You read off the operators in your spectrum by the powers of z that appear in this generating function. Okay, so the powers are the twist, turns out, the dimension minus the spin. That's not super important. Okay, and this is a really nice object because, okay, first of all, it's got this property of being analytic in the spin. So there's another inversion formula that integrates over Euclidean kinematics that doesn't have this property. And this is one of the original motivations for this, is it connects to Reggie physics, Reggie limit of scattering in the bulk, and put some previous work of Penadones and friends on a firm foundation by giving an analytic representation of the function of the spin. You can ask me about that afterwards if you're interested. It's also got this feature of being very interesting, that you might think that to get any individual pole here, you just put in the block that corresponds to it over there. If you just put in the block over here, then this formula doesn't make sense, or it doesn't give you the right kind of poles. It's really something that ties together the whole spectrum, and it uses nice asymptotic behavior, and it's not just a very simple formula that sort of gives you the poles term by term. It ties things together more in a more interesting way. So this, you might be familiar with something similar from dispersion relations in flat space, where you want to extract operator dimensions or Wilson coefficients by some integral over the S matrix kinematics, and you have to do some deformation of contours, and then you have to drop contours at infinity. And dropping contours at infinity is crucially important. It tells you that the states aren't arbitrary. They're tied together in some nice way, and the same thing is happening here. It's really analogous to those dispersion relations. Okay, and the other thing that will be important for us is that the d-disk, this object that appears, if you just put in a single t-channel double trace block, then it vanishes. Which means that if you're doing this in perturbation theory, which I'll just advertise, I won't explain any of the details here, but if you're doing perturbation theory, remember that really to leading order in perturbation theory, we need a Witten diagram, which has this full quantum thing, which is hard to calculate in general. But because these double traces drop out, we can actually plug just the classical piece in, and it gives us the right result. So, okay, you do this exercise. You have a great collaborator like Zara. This is a good opportunity to advertise that Zara's on the market, and maybe one of you watching on YouTube will have the opportunity to hire someone great this winter, so I definitely advocate for you to consider her carefully. She's really an expert in these sort of calculations, and she's not just done this stuff in the non-relativistic limit, but has got a lot of new results. So in particular, exchange of the stress tensor in general dimension, not in any limit. You know, this is a formula that you could use in 3D Ising model and so forth. You get something complicated. And you can match the results of these to time-independent perturbation theory. You know, again, something you learn from your first course in quantum mechanics, and everything works out. Okay, and the last thing I'll say, maybe I won't take too much more of your time, so I won't go through the details. I'm happy to explain afterwards how this all goes. But you can actually take this inversion formula, this is some CFT thing, and we'll just ask what happens if your correlator is governed by the non-relativistic regime. So you have large external dimensions and so forth. And then the whole thing reduces to something that's actually a lot simpler. There's a reason why I didn't write out what the kernels were in previous things. It's kind of complicated. So you get an integral that looks like this. There's, again, an integral over cross ratios. The only thing I'll point out here, first of all, is that we don't have the d-disk anymore. I can explain why the d-disk isn't there to anyone who's interested afterwards. But it's really just an integral of the correlation function. So we still have this property that the double traces drop out, that you, for example, to leading order in perturbation theory, the classical correlation function is good enough. That feature's still there, but it's not at all manifest. It's kind of mysterious how it works out that way. You can just check it in a few examples, and it kind of works, but it's sort of mysterious how that happens. The other thing is this object here. This is like in d equals 3, this is a bit like a Legendre polynomial. So it's, and the thing in the argument is the cosine of theta. It's the cosine of some scattering angle, roughly speaking. So it looks like the kind of thing that you would get by doing sort of the usual thing of picking out a particular spin by integrating against Legendre polynomials. But it's funny because the index is not the spin, but it's the other value of spin that gives you the same quadratic Casimir. And this is a signal that you're doing something a little bit different. It's not just that. It kind of comes from the fact that you're using Lorentzian kinematics in the original formula. So it's not something that is obvious how you would get it from the non-relativistic point of view. And in fact, we don't know at the moment how to derive this formula purely from the non-relativistic quantum mechanics. We just start from CFT and take a limit of the CFT formula. That's the only way we know how to get it. Yeah, and it's got these same properties that it ties together different states, relies crucially on what the asymptotics do. You can't invert sort of state by state. And yeah, it's just a very interesting object that you'd think that in non-relativistic quantum mechanics, it's been studied to death, that some dispersion relation like this, you would know about it, but it's, as far as we can tell, it's something that's completely new, and I think it's a fun thing to see what you can do with it. Okay, so there are various interesting directions to explore here. I'll just highlight the first one, is that I think there are a few examples that we're sort of starting to think about how we can really start seeing this regime in like n equals 4 or nice examples like that. This should be a sort of universal sector that appears in a lot of sort of top-down theories that we know about. And there are various other directions that are interesting to explore. Maybe one more is that this is quite a fun model as well for de Sitter space, where we're happy in AdS, where they've got the potential that looks like this, but you turn it upside down and you're sad because you don't know what to do in de Sitter space. And this is a really nice, clean example of where there's a lot of the physics we can talk about in de Sitter space, but just having an inverted harmonic oscillator is a fun model to just build a little bit of intuition in that context as well. So with that, I'll thank you for your attention and invite more questions. So this applies, first of all, the regime is when the external operator dimensions are large, but the energy you're considering is sort of order 1, let's say. So delta minus delta 1 plus delta 2 is not scaling with delta. And you want the spin to be of order 1 as well. And then the last thing you need is that outside this region of small cross ratio, it more or less looks like the free correlation function. You might be able to relax that. Okay, the important thing that happens here is that you rewrite the d-disk as a pair of contour integrals, where the contour runs along the real axis, round through the branch cut at z bar equals 1, and comes back again. And the important thing is you can actually deform this contour so that it sort of falls along a path of steepest descent. Okay, it's not close to the origin, where all the interesting stuff's going on. It's not really a path of steepest descent. But it goes, anyway, basically it's dominated by what happens in here. So you need like this calculation was done using the free correlator. So either it needs to be close to the free correlator, or at least you need to be able to neglect what's going on out here. So, okay, it's a little bit restrictive. Maybe I'll just mention that there's another regime that you can take here, which is, it's kind of similar, and you do this deformation to a different contour, but it's actually dominated by a saddle point, and that's when you take the dimension and the angular momentum to be both large. So this works in the non-relativistic limit, but also more generally. And that's something that's novel as well, and I think that's an interesting thing to explore a bit more.
So you take the dimension and the spin to be both large and their ratio to be order 1, or their ratio to be also goes
Yeah, so the ratio there, for this classical limit, the ratio can be order 1, can be held fixed. And in fact, yeah, so this interpolates, for example, there's a regime where the spin is much bigger than the dimension, which is the large spin regime that's been studied for a long time, Komagovsky and Zhibodev and Fitzpatrick and friends. And then there's a limit where the spin is much less than the dimension, which is our non-relativistic limit. And there's then some interpolation between them. And this classical thing, it gives you the interpolation between the two.